Welcome to the next lecture on the testing part of embedded system design, verification and test course. So, as we were seen in the last lecture that we are talking on the third part, which is on embedded system testing. So, in the last lecture we have seen the basic introduction to digital testing and what is the importance of digital testing in the context of embedded system design, verification and test flow. In the today's lecture, basically we will slightly go into details of the prerequisite module, that is on the introduction to testing. We will see today the concept of automatic test pattern generation. So, basically if you remember last lecture, what we had discussed is that as the all embedded systems basically use a digital platform for their computation, which is a major component of the embedded system design. So, there can be lot of faults which come due to the improper or due to some lacunas which are there in the fabrication process. To find out such faults, basically we have to go for testing. And we have seen that testing basically comprises of two parts. One is you have to plan basically what you are going to do the test, that is you have to decide what patterns you have to apply, what you will do, what do you want to measure, what is the golden response, etc. And the second part is the physical testing, that is you have to put the chip, you have to connect the equipments and measure. So, that is actually a more or less a clerical kind of a job, or in the other sense is more of a physical kind of a job. So, mainly we will be looking in this course on the test plan, that is given a circuit design or given a hardware component of the embedded systems, how do you plan to test it, that is what are the test patterns you will give, what you will measure, etc. So, in this lecture mainly we will be concentrating on given a circuit or a hardware component, then how do you automatically generate the test patterns. That is, how do you generate the test patterns means how do you plan for the test patterns which will be applied to perform physical testing. So, basically this is your, you can say that the digital test process, in which case in fact I should say that this is the physical testing process. So, this is the manufactured circuit under test, that is the physical circuit which has been manufactured, it will be put into a machine which is called an automatic test equipment, and then you apply inputs, you have the outputs. So, this is something called golden response. Golden response is basically for such given inputs, these should be the outputs if there is no problem in the circuits or there is no defects in the circuits, then for these inputs these should be the outputs. Now, you put the manufactured circuit in the tester, you apply these inputs physically, you measure the output and then you make a comparison. So, if this output matches with the golden response, then there is no problem in the circuit and it can be shipped to the customer. Now, this is the physical testing process, but today we are going to look at this and we are going to mainly look at this. That is basically how do you decide what test pattern to apply and how do you find out what are the golden responses, so that you have a test plan in picture before the devices is fabricated. So, once the device goes for fabrication, you have some amount of time. So, in that amount of time basically or even concurrently with the design process, you have to find out such sets. So, this is actually called test pattern generation, and if you are doing it automatically, we call it as an automatic test pattern generation. So, mainly this part of this course will be concentrating on how you can automatically generate test patterns or how can you do automatic test planning. That is the goal of the course, and this part actually, as I told you, is basically something physical, that you apply the test patterns, measure it and compare it. So, there is not much we can study over here. So, as I said, this is basically something called a automatic test equipment. So, we basically put these devices over here and there is a lot of internal computers and test pattern generation, test pattern analyzers inside. So, you have to just program that these are the test patterns to be applied, this is the golden response expected, it will do the automatic testing for you and it will just give a beep or non-beep saying that circuit is normal or circuit is having a fault. So, after that you give the test plans to this automatic test equipment, everything is very much automated. So, now we come to the concept of testing. So, basically are the test plans. So, let us assume that it is a 25 input AND gate circuit. So, there is a 25 will be the input, let me zoom in. So, basically it is a simple circuit in which case we have 25 input lines and 1 output lines and the output is bitwise AND for all the inputs. Now, say that I want to test it. So, basically how many inputs will be possible, as there are 25 input lines. So, it will be 2 to the power 25. So, many different input patterns can be possible and I have enumerated them. So, you can see all zeros to all ones, and for all cases the output will be 0 and excepting in the case of all ones the answer will be a 1. So, this is actually your golden response. Now, what will you do? Now, you will give all these test patterns to your test program and these are the expected golden response. Now, when this device will be fabricated, you will put in the tester will apply all these patterns, it will measure the output and actually it will compare with this. If all the bits are compared fine, out circuit is normal, else there is a fault. Now, the question arises, this is actually called functional testing, because there is a device, you want to apply all the patterns to verify that it is properly operating or not. In fact, as discussed earlier, testing can be very wide. We can start with functional testing, then we can go for speed testing, then we can go for power testing, then we can go for delay testing, then we can go for transistor level testing. It can be very wide, but for the practical sense, basically as I told you, we test for power, we test for delay, and we test for functionality. So today we will be mainly restricting to basically the functional testing part of it, automatic test pattern generation for the functional test. So in this case, all these patterns has to be applied and you will be able to do the test. So it is a very simple procedure. If there is a circuit of 100 inputs, you generate all possible input combinations, that will be 2 to the power n, get the basically the golden response, and you have to just report that these are all my test patterns, which is nothing but all possible combinations. The golden response you have to obtain by simulation or some other method, and then you have to give it to the tester. This is basically the idea of functional testing. Seems very easy. But now it is a very simple circuit with 25 inputs, all possible cases is 2 to the power 25. Now if you have a megahertz tester, because gigahertz testers also exist nowadays, megahertz testers people are not using, it is a slightly obsolete data, but I should tell you that there are very few companies in India, I think very few, maybe I know one of them which is called TESOLVE, which has such facilities in India. Mainly such facilities are generally in the Taiwan or such places where there are basically fab industries. But I should tell you that you have to purchase the time from the tester, because there are very expensive equipments and you have to pay the duty for using it. Maybe you say that I want to use the tester for 1 hour. You have to pay a huge amount of money to do this, because the testers are so expensive that to make profit, the testing vendors actually rent their machines, and the renting is in hours. So more time you spend on the tester, more money you have to pay. So our goal is mainly to do as much chip testing as possible within the given limit of time, because if you are taking more amount of tester time and you are able to test a few number of chips at that time, the cost of testing per unit chip will be higher. So our goal mainly is to use give less time of the tester and to test more number of chips in that time, so that the test cost per unit comes down. So if I have to apply all 2 to the power 25 patterns and assuming that is a megahertz tester, then time required is 33 seconds per chip. Means you have to apply half a minute for each chip, and generally there are around 1 million chips which are fabricated in a run, and you have to test all of them. So basically it will require some amount around this many days or years to check it. So it is an extremely difficult procedure and infeasible. So this is a simple 25 bits input. So a practical circuit will have 1024, or it can even have 64 bit inputs. So if you have to apply all 2 to the power 64 combinations, forget about 1 million samples. In years and millions of years also, you will not be able to test a single chip. So functional testing is very simple. Apply all 2 to the power 25 patterns or 2 to the power n patterns, where n is the number of inputs, all possible combinations you apply, match with the golden response, and you are super confident that your chip will function accurately as per the functionality. But again, 2 to the power n is an exponential complexity, and even for a simple AND gate you can see that exorbitant or infeasible numbers. So if the circuit has 2 to the power 64 inputs, you can do the mathematics, you will find that not even a single chip can be tested in a hundreds of years. So functional testing is very practical, but it is very theoretically fine, and you can guarantee that everything is proper only by full functional testing, but I am very sorry to tell that you cannot apply it practically. Then what to do? Because our job is to give guarantee to the as such, because 2 to the power n, this is full functional testing. This can give 100% guarantee that your chip will be operating fine if your testing is passed, but we do not have so many amount of time. So what we want to do? We want to bring it down, bring the number of test patterns down, but still we are trying to give a very good guarantee. Maybe this may be 100% guarantee, maybe instead of 2 to the power n, we will use only n, that is linear complexity, or even lower number of test patterns, and maybe the assurance level will come to 99% or even slightly less than 100%. But I cannot give assurance of 90% and sell the chips, not at all possible. So what do you mean by assurance here? As I discussed yesterday, say you manufacture 100 chips, you have to test them. You have to find out that 30 chips were abnormal, we throw them out, and 70 chips we sell it to the market saying that all are proper. So here is the assurance. When I say the 70% chips which I am selling to the market have no defects, there I should be absolutely proper. So there if I go for 90% error rate, then you are gone. That means basically out of the 70 chips which I am ascertaining to be having no faults, out of them again only 90% will be correct nature. Again 10%, that is out of 70, maybe around 7 chips will have defects which I am saying them to be normal. This is not actually allowed. So, assurance should be more than 99% plus. That is, when I declare say around 70 chips are normal from the 100 chips manufactured, among them in a very large sample maybe 1 or 2 may be wrongly binned. So, what do you mean by wrongly binned means I tell you to be proper, the tester tells that the chip is normal, you sell it to the market, but still it has a defect. So, that should be very low. So, that I mean by assuring the quality. Then it is a very simple story, I should not drag it longer, that functional testing is not practically possible. Then something came into picture which is very interesting, which is called structural testing, and he was the gentleman Earl, so who actually I gave the idea of structural testing. So, what he said is that basically functional testing is very complicated, huge time in consumption. So, he told that you basically test the circuit in terms of gates and interconnects. Do not test the functionality. Test the functionality only at the level of gates and interconnects. And he has shown that if you do this, of course, you are not going to give me as high guarantee as a functional test, but he has shown it by statistics applying it over millions and millions of test runs, that if I do such a philosophy that test the circuit at the gate level, functional level, and basically you you do not think about the full functional level testing, he has shown that the number of test patterns will come down drastically, but still the test quality or the test guarantee is more than 99.9% plus. So, the structural testing does not check the functionality of the entire circuit, rather it varies the structural part, that is the gates are fault free or not. That means, structural testing is a kind of functional testing at the gate level. That means, you will not test the circuit entirety itself, rather than each of the individual gates you will test in a functional level, and you will be forgetting that what the whole circuit does. Example is better. This is the same circuit, I have shown you 25 inputs and 1 output AND gate. Maybe it is made up of 5 individual AND gates of 5 inputs each. So, 1, 2, 3, 4, 5 gates, and this is the final AND gate, and this is the output. Now, say that I want to test each of the AND gates only at that level and not the integration. So, basically the G1, how many you will require? So, there are 5 inputs. So, you require this table, all combinations you require to do this. So, what is the time, what is the number of patterns? 2 to the power 5, that is equal to 32. Now, I will test this gate, I will test this gate, and I will test this gate, and my job is done. So, I will do it at individual level. I will test this gate, then this gate, and so forth. So, it will be 32 into 6, which is nothing but 12, 192. So, from 2 to the power 25, which is very large, I have come to 2 to the power 5 into 6, that is 192. So, huge jump. Basically, so that it is something like divide and conquer, or I should tell you that it is from 2 to the power n, we are from there we are going to 2 to the power n1 plus 2 to the power n2 dot, where n is equal to n1 plus n2 dot n. So, that means we are breaking down this n into smaller numbers. So, if you look at your simple algorithm and complexity theory, this brings down the complexity drastically. So, here on the example, I am testing all the gates individually, and I have to apply only 196 or in the range of 100 range patterns, whereas if I want to test the entire functionality is 2 to the power 25, which is extremely difficult. Huge jump in the number of test patterns. If you have huge jump in the reduction of these test patterns, then the test time will be very less, because now I will not apply 2 to the power 25 test patterns, I will just apply 196 test patterns and my job will be done. So, this is actually a structural testing. What is the cons? Basically, you are not testing the entire circuit functionality. But statistically, people have observed that whenever this gentleman actually proposed this idea, so he has not done any kind of mathematical analysis. Basically, he has tested this idea over hundreds and thousands of test runs and found out that if you still go for structural testing, your assurance quality is more than 90%, 99% plus. So, huge reduction in number of test patterns, but still slight compromise in the test quality. So, people started working for structural testing and it became a de facto standard. Now, certain issues start coming in. So, basically, sorry, this is so the number of test patterns required is 6 into 2 to the power 5 and basically 192, which is many fold smaller than load required for 2 to the power 5, and basically the time required for testing the circuit using 1 megahertz tester is so low, and for 1 million sample is just 16 seconds. So, it is very feasible. So, 1 million samples can be tested in just 16 seconds. So, structural testing became highly beneficial over functional testing. but there are some penalties, because engineering is never a magic. You do some optimization, you have to pay cost at the other end. So, what is the cost? Now, let us look at this circuit. So, I think you might have all seen your dual inline package chips, that are the black chips with some legs outside. That is the normal ICs. Whenever you open the motherboard of the computer, you have seen that some ICs, black colored chips are there. Basically, what I am trying to say is that this part is basically sealed. This is sealed in a wrapper. So, this is the black structure we always see in the dual inline packages of some chips, and you see some pin out. So, basically this part is black box and they are highly sealed. So, if you have to test these gates, say, so you will apply patterns over here, there is no problem, but how do you measure this output? Similarly, how do you measure this output? How do you measure this output? Now, this is a problem. Secondly, when I have to test this gate number 6, this observation is fine, but how do I apply patterns over here directly? How do I do it? Because these are combined lines and this is the structure is closed. So, how do I have access to it? So, it is called structural testing has the problem of observability and controllability. Difficult to observe this line, difficult to observe this line as well as difficult to control this line. How do I do this? Because they are packed. So, I have to somehow make pin out extra. Obviously, the reason is there is no other solution, you have to bring out extra pins or you should have extra arrangement to control such internal lines. Then only you will be able to do structural testing, because I am doing all the gate testing individually. So, therefore, I should have full access to these gates, but as this is a closed box, so I do not have access to some of the pins. So, that is actually called observability and controllability problem. So, one main issue is that, now let us look at the penalties of structural testing. Each individual gate is tested, however, the integration is not tested, but that is a minor issue, because already by handling large number of cases, people have found out that the compromise is not a much. But to test individual gates, controlling and observing values of intermediary nates becomes mandatory, which had to extra pin and hardware, that I will tell you. This is a major problem, that how do you access the internal lines, and to add test internal lines, as I will show you, you will require extra pins and some multiplexing arrangements. So, for each individual internal line which has to be controlled and observed, you have to put some extra circuits. So, circuit with 1 million internal lines require some million amount of multiplexer and large number of extra pins. So, that is actually a killing point. With an example I will show you. So, let me zoom this part. So, as we know, this is the output of this gate and you have to observe this line, and also you have to, for the testing of gate G6, you have to control this line. That is, you have to give input directly. Right. So, for example, to do this, we actually put something called a 2:1 multiplexer. So, assume that this is the normal output of a circuit and this is some extra test pin, this is your test pin, and this is your normal circuit output, circuit line. We actually do is we put a 2:1 multiplexer, and there is something called a test mode, and this is the mux output. So, when the circuit is operating normally, I am not interested to do test, I will put 0 in the test mode. So, this line will be connected to and your circuit will be operating properly. And whenever I want to do test, what I will do is, I will make this line as 1 and this part of the line will be connected to the output. So, circuit output will be blocked, and from the test pin I can give any input which will be going to the gate to be tested. So, such an arrangement I have to make, and this arrangement is already displayed over here. So, for example, I want to test the circuit, I will make test mode equal to 1. I am assuming that I am testing gate number 6. So, I make a test mode. So, this multiplexer, this is line, sorry, I made a mistake. So, basically test mode 0 means it is in a testing, I am doing testing, and 1 means I am doing a normal mode. 1 means normal and 0 means test. I think just if you flip the bits of the multiplexer, the same thing you can do in the other way around. In this circuit, 1 means normal, 0 means test. So, I want to do a test, so I will make the basically test mode multiplexer value equal to 0, the select line. So, of course, if you see, so this line will not be in position to continue. So, this line will be cut because it is 0. So, the output of AND gate 1 cannot go to the input of gate 6, but this is the test pin which is now excited because it is going over here and it is going through this one. So, you can easily apply any pattern to the gate number 6 directly bypassing G1. Similarly, for the other pin also, basically if you look at it, this will be cut and this line will be going at the input. So, by this multiplexing mode you can directly give all the test patterns to the gate number 6 without having to be buffered by G1 and G6. So, you are bypassing this entire part and you are directly giving it as a output. You are giving the test patterns directly to the G6. Now, say that I want to operate the circuit in a normal mode and I am not doing testing at this point. You make this gate equal to test mode equal to 1. So, this one will be connected over here, this one will be connected over here. So, automatically circuit is in your normal operating system mode, right. So, this is the way we are doing a control. So, this is how all internal lines has to be controlled, because otherwise your normal circuit gates will start probing your gate pattern, because here I want to apply 1, 0, 1 my test patterns, but if I am not able to block this gate, then I will not be able to directly apply the test patterns to the gate under test. This is your gate under test. So, this is how actually I can make the lines controllable by putting 2:1 multiplexers. Now, again, but here for the gate 6 I apply all the patterns and observation is no problem, but if you just think about the testing of this gate, this gate, then basically the problem is other way around. That is, I will be able to control these lines very easily, but how do I observe these lines as the output? So, this is not a very difficult problem, you just put out some extra pinouts, which are the test pinouts. So, in this case whatever the test mode maybe made to be 0 and 1, I do not bother in this case, but some extra pinouts I will make for such gates. Because for observation controlling is more difficult, because for controlling you have to stop the input from the normal circuit and you have to have a test pins which can give the value to the gate under test. But for observation this is going to this output, I have no problem, you just put some extra pinouts from these gates. So, you can directly observe them as the output. So, now what are the costs I am paying to go for structural testing? I have to have whatever intermediate lines you want to test, because I am testing this gate, I am testing this gate at individual level. So, these are some intermediate lines which I have to test, so extra pinouts I have to bring. And if there is a gate which is internal, which I have to test it, so I have to put some extra multiplexers so that I can control these lines. So, there are a lot of extra output lines which will be coming out of the intermediate lines. So, if there are n intermediate lines which has to be observed, so n extra IO lines will be brought out for observation, and if there are k internal lines which has to be controlled, so therefore, there will be k 2:1 multiplexers this way plus k extra input lines which will be your test input lines, and there is one test mode pin. So, you can easily understand, if there is hundreds and thousands of such internal lines which has to be controlled and observed, how many extra pinouts and how many extra multiplexers has to be put. Extremely difficult, because your circuit cannot have a huge number of IO pins, because that is blocked by the area of your chip covering material. This is the inline package. So, your chip is packaged. Before selling it to the market, your chip is packaged, inside there will be the die. So, of course, this is not very large, it is maybe 5 centimeters by 5 centimeters, 4 centimeters by 4 centimeters or something like that, but we cannot have n number of lines. These lines are generally restricted to 48, 64, if it is a ball grid array package it can be in the level of high hundreds and so forth, but you cannot have more than millions, such order of millions of IO lines. But if you see structural testing and if you have to do internally, you have to probe the pins and you have to control the lines, millions of extra IO pins will be there. So, structural testing also hit a bottleneck. But what happened is that it has given a very good insight that if you go for full functional test is a huge problem, you cannot do that. Structural testing opened up an avenue that you need not test the circuit in entirety, basically you test the individual gates itself, still the test coverage is or test confidence is very high. But the problem is that very much amount of extra pinout is required. How do you handle this? So, it opened an avenue and also it reached a bottleneck. Then something extremely interesting came up, but again I have to emphasize one part here. In all these cases, basically people have not done any kind of mathematical analysis to prove that what is the confidence I will get with compromised amount of testing. Basically people have found out functional testing 2 to the power n, structural testing n, but the confidence I get is very near to in both of them. One may be 100%, other may be 99.9% plus. This they have done by statistical finding. They have done hundreds or millions of different test runs and they have found out that structural testing is almost equivalent to functional testing in terms of confidence, but the number of test patterns to be applied is very less. So, that way they have found out that they are very correlated. It is not a pure mathematical way of determining. They have done basically by testing and statistical results and hundreds of hands-on experiments. But the structural testing opened up an avenue where people started thinking that we can still go for testing without thinking of functionality directly at a structural level, but it hit a bottleneck or hit the wall when basically we found out that so many extra pinouts will be required. Then some people improvised on it and they landed into something called a fault model. That is, now even I will not test the functionality of the gates. So, initially full functionality, then I came to functionality of the gates. Then people started thinking why I should test functionality of the gates. Let me try by something like I will not even test the functionality of the gates. They said that can I find out certain cases which are happening more prompt, that is such circuits are there, they are having some kind of defects. Can I somehow pinpoint or find out which are the most probable defects and I assume that to be my standard fault models. That is, maybe there are a lot of devices which we have in our daily life. Most of the things have some kind of failures, but if you study in depth, you will find out that for this class of systems, this is one of the most important failure it has. This is another system and the class of system, and it suffers from, this is the peculiar fault it is, but it is more prone to such type of faults. So, can I have such kinds of what is called as fault models? That is, they are some of the standard defects which the chips are most likely to suffer from. So, they started thinking of some directions like fault models. So, structural testing with fault models involves verifying each unit is free from the faults of the fault model. That is, basically now they will not test the functionality of the gates, rather they know from statistics that these gates is most likely to suffer from these faults. So, our job will be just to find out that the gates are free of those faults or not even going for functional test. We will give more examples to elaborate on the concept. A model is an abstract representation of a system. Modeling reduces complexity in representation, but captures all properties of the original system required for the application in question. This is very important. What is a model? That means, as I told you in the last class, faults can be of fault can be of huge nature, functional, structural, delay, silicon level, manufacturing level, so many different type of faults can be possible. But can we restrict our models? That is, for a digital functionality of a circuit, what are the most possible fault models or most likely fault models your circuit is going to suffer. So, our application in this case is embedded systems and operating in a digital mode of operation. So, what are the most typical type of faults my circuit can suffer from, and I will only verify that my circuit does not have such faults. Then I can be more or less confident that the circuit does not have any problem. But again people have found out statistically that from functional to structural to structural with fault models, you are having some ease in testing, but actually there will be slightly compromise. Like for example, 100% to 99.99%, here it may be 99.98%, slight reduction in fault quality will be there. But of course, that quality drop cannot be very huge, like from 100 to 90 and then 90 to 80, such kind of drops with different fault testing strategies is not actually allowed. The compromise will be very less, but the ease of testing, the time to take in for testing should be coming down drastically. So, fault modeling was the key buzzword, and actually it has solved most of the problems in testing. People have statistically found out that you need not test the functionality of the gates even, rather you try to find out a good quality fault model which mostly the gates suffered from, and try to verify that such faults do not exist in the gates at all. And if you establish that point by testing, then there is 99.98 or 99.99% assurance that there is no, means you are not selling a bad chip to a customer telling that it is having no defects, that is your binning is proper. So, a fault model is an abstraction of the real defects in the silicon such that the fault models are easy to represent, because I cannot give high complexity fault models so that you take years to generate the test patterns, and also huge number of test patterns are generated, that is also not allowed, and it should ensure that one verifies that no faults of the fault models are there in the circuit, quality of test solution is maintained. And if I somehow verify that no such faults of the model are present, then quality is more than 99.9% plus. So, let us take an AND gate and basically say that somehow you are not able to dope this. Certain problem is that this is open, basically this line is open. So, this unconnected net is the defect. So, this is basically your defect, that somehow you are not able to manufacturing, this is a problem. Error is, now what is an error? When you apply all these as 1, 1, 1, 1, 1, but output gate is actually 0, whereas it should be a 1 because this is open. So, basically this is one type of a defect. There can be n number of defects, like this may be getting shorted, right. Then basically what may happen, even these two lines get shorted, then this line can also be an open, this line can be also an open. So, there are n number of different type of defects which is possible. So, this is your basically defect. What is an error? Defect is basically your physical defect that happens during fabrication. Error is the logical manifestation, and what is a fault, which is our model. So, basically our this is what is real defect at silicon level. This is your functional Boolean function, what happens, because you are talking about digital circuits. But fault or the fault model is that you will find out that this line is stuck at 0. That means, whenever you are applying all ones or whatever, this line basically is, if you apply a 1, still a 0 will be there, and also the output line will be 0 stuck. So, that is, we call that this line is stuck at 0 and this line is also stuck at 0. So, this is actually a fault model. So, the real defect is you have not been able to properly dope the silicon, dope with copper. It may also happen that the copper is very thin, voltage is not passing. It can also happen that there is some problem with the vias. N number of different type of defects are there, but the resultant is you apply a 1 over here, this 1 is actually not passing it over here, and all ones you are getting the value 0 over here, which is the error. That is your Boolean manifestation. And what is the fault model? The fault model is this line is stuck at 0 and this line is also stuck at 0. Stuck at 0 means even if I apply a 1, the value will be remaining at 0. So, this defect can be enormous. It can be also at some point, it can also be due to some kind of manufacturing problem in the transistor which is inside your AND gate. That can also lead to that this line, means if you are giving a 1, this is not actually passing to the output. But we will abstract everything out. We will just assume that such a representation is stuck at 0 for this line as well as for this line. So, this is actually called a fault model. So, people have found out different type of fault models which are very much closely related to the defects. But if you really think of defects, the Pandora's box will open up. So, people have found out that defects can be many, it can be wide, it can be at the net level, it can be at the transistor level, it can be at so many different places. But how do you abstract it as a model? So, they are easy to represent and it is easy to test, still the quality of assurance is high. So, by studying all these defects at the silicon level and device physics level, people have found out many popular and widely accepted fault models. How do you make it widely accepted? Statistical experiments. So, what is one of the very important one is called the stuck at fault model. That is, they assume that each net will be either stuck at 0 or stuck at 1. There is something called delay fault model, that is this slide, the time taken to go from 0 to 1 is higher than the rate, and this is delay to fall from 1 to 0. The time taken for this fall is basically higher than the specified time rate. Bridging fault, between two gates there can be a short, the short can be AND short or an OR short. This is, after this short, basically this line will be behaving like this. These two independent lines, but due to some shorts it will be behaving either AND short or it will be behaving like an OR short. There are different type of fault models, but these are the most accepted ones. Now, your job, as we will see, is just to verify that none of the gates have, in current discussion, basically we will be studying only on this. Whenever we will be talking about advanced fault models in this lecture, in this course, we will go for such more kind of advanced faults. But today our discussion is mainly limited to stuck at faults, because this is the most widely accepted, and till about last 15 years back, this was the only fault model practiced. With more sophistication in fabrication technology, slightly more is improved, or advanced fault models are also had to be considered. So, stuck at fault model is very simple. You assume there is a line, the line is either stuck at 0 or stuck at 1. So, it captures a huge number of defects. Now, what you have to do? You have to just verify that none of the circuit lines is having a stuck at 0 or stuck at 1 problem. So, this is basically your, I am giving with a circuit as an example. There is certain small interesting example here. So, this is the look at this fan out, this is your fan out. So, as expected, you will just say that either this line will have stuck at 0 or stuck at 1. There are the two faults possible. But if you see these are continuous line, still basically you are assuming this fan out to be independent and this fan out to be independent. What do I mean by this? That is, I have to consider this fan out stuck at 0 and stuck at 1 possibility, and also I have to also consider this fan out branch independently and also this fan out branch independently. Now, why? This is because people have found out that if you are assuming that such faults are not possible, only this line can be stuck at 0 and stuck at 1, there is certain quality in the correlation. Because as I told you, these fault models are just abstraction. So, you assume that they stuck at 0, stuck at 1, stuck at 0, stuck at 1. So, all these lines will be having stuck at 0 or stuck at 1 faults. I will try to ensure that none of the lines is having a stack at 0 and stack at 1. I will also do it for OG1, but logically looking at as the continuous net, I can drop these fan outs. But if you do this, we will have statistically found out that the quality of test comes down. These are statistical, again I am telling you, all these fault models have been coming out from the statistical improvisation. It is not by, statistical findings, it is not by any theory. So therefore, along with this, you have to also think about these two lines as independent, all fan out lines will be independent, and you have to ensure that none of these fan out lines or the normal lines or these ordinary lines should have a stack at 0 or a stack at 1. So you have to apply test patterns and ascertain that none of the lines are either stack at 0 and stack at 1. If you can do this, then you can be 99.999% sure at least the circuit is having no defects. So this is something called a stack at fault model, which is very much unpopular, and the basic model we can start our teaching with. So this is what is the assumption, you can look at it. Now there are very interesting cases. So how many at a time, how many lines we will take? So people always call it a single stack at fault model. That means I will assume that only this line can be stack at 0 or stack at 1 fault, and I will find out test patterns to verify it. But I will not take an assumption that these two lines can be stack at 1 or stack at 0 at a time. I can do that, but in this case, what is the number of possibilities? If there are n lines, then there can be 3 to the power n minus 1 possible stack at line combinations. That is, 2 lines can have stack, any 2 lines, any 3 lines, any 4 lines, any 5 lines can be having a stack at 0 and stack at 1. Like these 2 lines can have, if I assume that any 2 lines can be stack at 0 or stack at 1 together. So the number of combination is these 2 will be a combination, these 2 will be a combination, these 2 will be a combination, and so forth. Huge number of such combinations will come up. Then also you can think 3 lines can also be stack at 1 or stack at 0 at a time. Then the such number of faults will be very, very large, and it is 2 to the power n minus 1. So this is actually called multiple stack at fault model. So due to the increase in this complexity, people have dropped this multiple stack at fault model concept. Their single stack at fault model is manageable in number and also provide acceptable test quality solution, and it is the most accepted fault model. There is no problem that if you assume multiple combinations, but the number of faults will be so high so that you will end up in generating more number of test patterns, and the main goal of reducing the number of test patterns or number of test pattern generation time will be gone. So therefore, with slight compromise in quality, we will assume that at a point only one of the lines can be stack at fault, but all lines have to be tested. First we assume that this line is stack at fault, test it whether the stack at fault is there or not, you repeat for this, repeat for this, repeat for this, all these lines you repeat one by one at a time. But at no point of time you will assume that there can be combinations. So, but in reality there can be combinations, because if you assume that this line can be stacked, why not this line? But people have found out that doing this may slightly increase the test quality, but it will not have too much impact on but the amount of impact on test generation time and the number of faults is so high that the benefit will be nullified. So therefore, people go for this model. Only one net is fault at a time, the net is permanently either stack at 0 or all branches of the fan out are independent with respect to the locations, and after a stack fault. That is, you have to consider these and these 2 lines independently. So handling multiple stack at fault in a typical circuit with hundreds of lines is infeasible, although it may give you a better accuracy, but this is not possible. So now examples, we will see the benefits. So what was the structural fault benefit? Structural test benefit was you need not apply 2 to the power n combination, it is much lower, but the problem was you have to probe lot of internal lines. Structural testing with fault models actually alleviated this probing business. We will see how. So if you can, that is our goal. Structural testing is very good, but only problem is that you have to probe out lines. If somehow that can be alleviated, then our job, if that can be nullified, then we are in the winning position. So assuming that I have to do testing of this AND gates. So you have to check that none of these lines are having stack at 0 or stack at 1 at a time. So individually you have to start one line at a time. Assuming that this is the first line you are taking, which this line is assuming to be a stack at 0. So if it is a stack at 0, of course what you have to do, you have to apply a 1 over here. So if the 1 means if this line is normal, so 1 will pass over, and if the normal line is 0, it will be a 0 effect. And of course all other lines has to be a 1, of course, because if any of the lines is 0, so this line will be nullified. Before, if I make I5 equal to 0, whatever be the case with this line fault or non-fault, the output of the AND gate 0 1 AND gate of G1 output will be 0, and I cannot do anything. So I have to make all these lines as 1, so this is actually sensitized and I can look at the fault value. Similarly, this gate output has to be coming out over here, because importantly I cannot probe any of these lines, I cannot probe. I can only probe these lines and I can only put control values over these lines. So, I have to observe this fault impact at this point of time. So, what I have to do? So, if any of these input lines is a 0 to the AND gate, the output will be a 0 irrespective of the fault effect. So, I cannot have I cannot afford to do that. So, what I have to do? I have to make all these lines 1. So, if I am able to do this, and in fact all these lines I have made 1. So, this line is actually sensitized to the output, so that I can observe it directly. The implication is I make all these lines as 1s, that is all these lines as 1 will allow me to see this value of this line at the output without having to put any kind of probes in between. That is the advantage of fault model based testing, that I do not need any probe over here, but still I can see the value at the output. Now, I put a 1 over here and all 1s over here. So, if the circuit is normal, you will get the output as a 1 over here. If the circuit is having a stuck at 0 fault over here, you will get a 0. So, the output will be something like this, 0 if there is a fault and 1 if there is not a fault. So, basically this is your test pattern, all 1s. All 1s is your test pattern, and if I am observing 1 at the output, you can be very much sure that it is not a stuck at 0 at 1 fault. This is done. Now, another interesting advantage of structural testing with fault model comes. You can easily observe that this pattern not only tests the stuck at 0 fault, but it will test the stuck at 0 fault here, 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 here. All the lines will be ascertained not to have a stuck at fault. That means, the single test pattern actually tests multiple stuck at 0 faults in this circuit. So, that is one very interesting phenomena which people have found out, that if you are able to test the circuits with fault models, basically one test pattern will test multiple fault models. So, here one test pattern is testing all the stuck at 0 faults. I do the repetition with a different fault, because each line has to be tested with a stuck at 0 or stuck at 1. But with the all 1 pattern, I have tested stuck at 0 at all the lines. Now, my testing for stuck at 0 is over. Now, I am taking a stuck at 1 fault over here. Now, what I have to do? Again, I have to put all the lines as a 1, because all the inputs of these AND gates should be a 1, otherwise the fault effect will not propagate. Now, this is stuck at 1, so I will have to of course put a 0 over here. So, 1 if there is a fault, because normally it is 0, so 0 should pass over here, but if it is stuck at 1, the answer is a 1, and basically if 1 there is a stuck at 1 fault over here, otherwise 0 is not a fault. So, in this case this line basically tests a stuck at 1 fault over here, this one also will test a stuck at 1 fault over here, as well as it will also a stuck at 1 fault here. Interestingly, when I am testing this stuck at 1 fault, I am assuming that this is the only stuck at fault which is existing, these are non-existent. Now, the next will be I will eliminate this. I will assume that there is a stuck at 1 fault at this point I want to test it. You will be interested to observe that the same test pattern can be applied basically. Similarly, next what I will do is that next I can eliminate this and assume that this is the only line which is having a stuck at 1 fault over here. Of course, the same pattern will do the test. Indirectly, what it means, this test pattern will test stuck at 1 here, stuck at 1 here, and stuck at 1 here. So, one test pattern here test for 3 stuck at 1 faults. Now, if I want to repeat this for this line stuck at 1, so your answer will be 1 0 1 1 1 1 1 1. Repeating in this manner, you will find out that there is 25 lines. So, 25 running combinations like 0 1 1 1 1, then 1 0. 25 such patterns will test the whole circuit for all points stuck at 1. So, 25 plus 1, 26 patterns will prove that there is no stuck at faults. So, we started from 2 to the power 25, then we came to 196, and now we have come to 26 number of test patterns. So, this jump is very well established, because for this first work we said that we can do structural testing, still we can have very high correlation with functional test. But the problem was that you have to put lot of multiplexing arrangements. Then we came here with stuck at fault models or fault models. Then we have found out that this number is also coming down, and also more importantly would not need extra pinouts. So, therefore, structural testing with fault models became a de facto standard, and all testing now in case of embedded system hardware or pure VLSI hardware are with structural fault models, and structural testing with the concept of fault models. So, this example you can look at it. So, in structural testing, one stuck at fault model, with stuck at fault model one test pattern can test more than one fault. So, that is another benefit of structural testing with fault models. So, again comparing Pros is no extra pinouts or DFT circuits. DFT circuit means extra circuits which you have to put it to ease testing. Multiplexer, shift register, nothing is required. Low test time, as one test pattern can test multiple faults. Problems are functionality is not tested, not even at the gate levels. So, in structural testing we do not test the functionality of even the gates. At least structural testing was testing at the gate level functionality, but here we have totally thrown out the functionalities of the gates. However, testing history or statistics reveal that even with this price space, the quality of solution is maintained, that is slightly compromised in test quality. So, therefore, this was a huge revolution in testing, that I can test at structural level with fault models, but still the compromise in quality is much less. So, this is the comparison. Functional test is without fault models, structural test is with fault models. Functional test, manually generated test patterns, basically we never apply 2 to the power 25, so or 2 to the power n, basically people restrict it to a less number by manually intervening. That is, you know the functionality of the circuit, you know what test patterns to test it. Thus, they can be taken from the verification phase. So, functional testing can still be done without 2 to the power n, but lot of manual intervention is required to tell which test patterns to apply. Slow and labor intensive, fault cover is not known, more number of test patterns and cannot be applied at the operating speed. So, those things we will see later, but the idea is that huge number, and in fact, if you want to reduce it, you have to manually find out which are the most important test patterns. Structural testing is with fault models, you can always apply algorithms to generate the test patterns, because you know that we need not at all look at the functionality of the circuit, just the structure of the circuit is there. Stacked fault model is there, you have to find out which test patterns can verify that none of the faults are there. Today we will also see some of the ATPG kind of algorithms. Efficient and automated, fault coverage is a quantified metric. That means, here if I say that I have functionally tested your circuit, what do I mean by that? Have you applied 2 to the power n? Not possible. Then you have to tell the engineer knows the functionality of the circuit and he has applied the most important test patterns to check it. So, there is no quality, not quantitative verification, quantitative guarantee, but here I can tell that I have tested the circuit with 100% coverage for stacked faults, and we know that if somebody has done such a testing with 100% coverage for stacked faults, the accuracy is 99.9 plus. So, you know that if I am selling 1 million chips, a very few of them will be wrongly bent. So, this assurance is given to the customer. Less test patterns, and basically these are the points we will see later basically. So, this is what is the advantage of structural testing with fault models. Now, the second concept, that given a fault model in a given circuit, will I manually generate the test patterns? Is it possible? No. In functional testing, there is no solution, because the engineer has to know the functionality of the circuit and he has to generate the test patterns manually. But in case of structural testing with fault models, we can automate it. So, this is actually called automatic test pattern generation algorithms. The algorithm will generate the test patterns for you. So, what it is, something like stacked 1. So, if the circuit is stacked 1, you have to always apply a 0 to it. Then you have to propagate the value to the output. So, you have to propagate the value to the output, means this is the AND gate. So, all other inputs to be 1. So, this we are calling as propagation, simple graph traversal. So, 0 means sensitization, it will come to the output, all other lines has to be 1. So, then you have to find out to make this line 1, what are the this should be the case and so forth, and this line is 0. So, how can you make this line as 0? So, it can be either 0, 1, 1, 1, or it can be all zeros or any of the pattern. So, whatever I was doing like this is a simple graph traversal with Boolean function manipulation will give you the test patterns to test the stacked faults. So, this is actually called automatic test pattern generation and is a 3-phase algorithm. Sensitize whatever in the stack, you apply a given value, propagate the value to the output so that you can observe, and now justify these requirements, that is all ones or some values will do it. So, this is actually called a 3-phase test pattern generation algorithm, and I can easily write a C code to implement it. In fact, there are a lot of CAD tools like Synopsys, Tetramax, a lot of open source tools also. If you give the circuits and the fault model, automatically the test patterns will be told to you. So, what I was telling is a 3-phase algorithm: fault sensitization, fault propagation and justification. Sensitize means stacked 1 you apply 0 and vice versa. Propagation means the fault effect has to be propagated to the primary output, and justification means you have to go back so that these whatever lines I want these values. So, what are the primary input values I have to keep. So, these are, but it is not as green as there can be lot of conflicts. So, if there are conflicts, we have to apply a different test patterns to solve it. I will take examples. Like in this case, basically if you see, for justification I require all ones over here. So, there is only one solution, all ones over here, but I require a 0 over here. How many different patterns can be possible for this gate? It can be all zeros or it can be 0, 1, 1, 1. So, any pattern except all ones. So, except this, any pattern can be applied to get a 0 over here. So, there is some kind of conflict. Conflict means you require a 1, for this you may require a line, this line to be 1, but for some other purpose this line cannot be 1. So, there can be conflicts. So, to have, and then you have to reiterate, you have to find out another way to generate the test pattern. So, it is not always green, sometimes there will be conflicts, then you have to again reiterate and find out which test patterns can be able to test it. But again one important thing is that for some faults there cannot be any test patterns. So, in that case you will keep on iterating and finally you will declare that there is no test patterns to find, there is no test pattern to test that fault, and that fault is basically a redundant fault. But anyway, there are some stray cases and not much emphasizing in this course, because these things are well elaborated in any kind of standard digital testing course. But the idea is that I am trying to say that sensitize, propagate and justify is the approach to generate a test pattern, but sometimes there can be conflicts, in which case you have to reiterate and find out a new test pattern. But for some faults, even after a lot of full reiterations, you will find out that there is no patterns which can test it, and such faults are called as non-detectable faults. So, this is the 3-phase algorithm. Okay. So, how do you do this? Now, there is a very interesting concept. So, in this case if you see how many faults are there, there can be 25 lines, 25, 26, 27, 28, some 30, maybe say 30, how many, 25, 30, 31 lines in this case. So, how many stacked faults can be possible? 2 into 31. So, around 60 stacked faults will be there, stacked 0 and stacked 1. Now, what I have to do? I have to do it for all the lines. All the lines I have to find out, take a fault, test it. Take a fault, generate the test pattern by this sensitize, propagate and justify algorithm. So, if the circuit is very big, so this iteration has to be done for all the lines into 2, because each line can have a stacked 0 and stacked 1. But people have found out not required to do like that. Even there is some approach called random test pattern generation. That is, you just randomly apply some patterns and see how many faults are getting tested. Or given some random patterns, you find out how many faults will be tested if I apply those random patterns. And then some faults will still remain, which we call difficult to test faults. For those, of course, you have to go for this deterministic test pattern generation by sensitize, propagate and justify. There is a very simple example, interesting and funny example. Say if you go to a fair and there is a mela, that is a fair, if you go, there is a lot of balloons in the screen and you have to take a gun and you have to shoot down the balloons. So, say that there are around 100 balloons which are in the screen. So, initially and you have to shoot down all. So, what will be your approach? You will randomly start firing. So, most of the balloons will be blasted and only few of them will remain. For them you have to go for aim and shoot. The same thing happens for testing. That if there are all faults to be tested, instead of just going for sensitize, propagate and justify algorithm, that is aimed shooting, do not go by that. Apply some random patterns and see how many faults get tested. After a certain amount of time, you will find out that even after applying random patterns, some faults are not being tested. That means they are difficult to test faults and untestable faults. So, you have to take one by one such faults and go for sensitize, propagate and justify based faults. So, justify based testing. All faults will be covered by that scheme, except few will remain or few may remain which are non-testable faults. So, we go by this. So, for example, I assume that I have to test this circuit, and I apply a random pattern like 1 0 0 1 1 and 1. You will find out that stacked 1 fault of this one is tested, stacked 1 fault of this one is tested. You take another random input like this. All stacked 0 faults in the nest are tested. So, how many? Some 30 faults are tested and some faults are tested. Go by this. So, randomly I apply this pattern and find out which faults get tested. These are the 2 faults getting tested. I apply all ones as a random pattern, because randomly some arbitrary random pattern you generate and apply and see how many faults get covered. If this is generated randomly, you will find out that stacked 0 faults in all nets are covered. Generally, in random test patterns also we sometimes apply some deterministic ideas, that we always use all 0 and all 1 patterns to go for testing, because they have slightly high coverages. But these are some offshoots from the algorithm. But for a very normal situation, you just say I apply random patterns, maybe these are the 2 random patterns generated I applied, I found out that these are the faults already covered. I will keep on doing it with random patterns and finally I will find that now there is no improvement. That is, from one random pattern to the next random pattern, the number of extra faults being detected is becoming less. So, at that time I will stop and start applying this sensitize, propagate and justify approach. So, with this deterministic algorithm is not required to be applied for all cases. It will be required only for difficult to test faults and untestable faults. So, basically what is the algorithm? Generate a random pattern, determine the output of the circuit for that random pattern as inputs. Take faults from the fault list and modify the Boolean functionality of the gates, put inputs as the faults. That is what I am doing. I am taking a random pattern, I am applying this to this one. I find out the normal values. Then I take one fault at a time and I change the Boolean values, and I find out which faults are getting detected by the random patterns. Those faults I will keep on deleting from my fault list. Like in this case, this example, we have found out that these two random patterns is detecting this fault, and easily I can find out by modifying the Boolean functions over here. That is, even if you forget about the idea of manipulating Boolean functions, you can just see that I randomly generate test patterns and find out which faults are getting detected. This I go by comparing with the normal output of the circuit for that given random pattern, and whichever faults are getting detected by difference in the output values in the fault case versus normal case, those faults you can remove. And finally, it keep on doing it till you find out that basically the number of extra test patterns, extra faults getting per new test pattern is not very high. Determine the output of the circuit with fault for that random pattern. If the output of the normal circuit varies from the one with fault, then that random pattern detected fault under consideration. If the fault is detected, remove from the list. These are repeated for another fault in the list. This continues till all faults are considered. You take a random pattern, find out the normal value. Find out which faults are getting detected by the random pattern. Simple, you take one fault at a time, apply the random pattern. If the output of the circuit is different from the normal one, that fault is detected. Else, this fault is not detected by this random pattern. You keep on doing it for all the faults. Which faults are detected, you throw them out. And next, you take another random pattern and repeat the same procedure with the number of faults remaining. You keep on doing it, then you will find out. Basically, this is the diagram which shows this, a random pattern, normal circuit with fault 1, 2 and 3, you simulate with the random pattern. If there is a mismatch, that fault is detected, and then these faults will be thrown out from the list, and again you have to repeat for a different random pattern. Very simple logic. After some time, you will find out that with new test patterns, the number of faults being detected will become very high. But after a certain amount of time, you will find out that even with new number of random patterns, this is almost flat or slight increase. That is, first random pattern you take, 100 faults get detected. Second random pattern you take, another 100 faults detected. Then 80, then 70. New faults will get detected by the one more new test random pattern you are taking. But after a certain amount of time, you will find out that when there will be very less amount of faults remaining, with a new test pattern, the number of random test pattern, the new faults getting detected will be very less. So at that point, we will stop and we will start applying sensitize, propagate and justify approach to test those faults. So basically, that is what is the most critical part of testing, because random test pattern generation is very simple. Just generate a pattern, find out which fault is there. So that is why we say that test pattern generation is done in two phases. One is a random manner, in whichever faults are remaining, you have to apply sensitize, propagate and justify approach. And also more than 99.9999% of faults will be detected by these two phases, but few faults may remain undetected because they are non-testable faults, and that you will be only able to find out by this approach. So this is what is the basically this is called path sensitization based ATPG, that is sensitization, propagation and justification. So with this 3-phase algorithm, we can find out the faults, how the faults can be tested which are difficult in nature. Now I will give you an example which will clear basically how test patterns can be generated for in the 3-phase algorithm which is called the deterministic test pattern. Before that, there is some Routh's 5-value algebra you have to know. 0 means 0 0, 1 means 1 1, x means x x, x means, say for example, this AND gate, the input is 0 and this input I do not know, the output is x, that is an unknown input. There is something, these are the two things we generally introduce apart from normal Boolean algebra, D and D bar. So D means what? D means normally the line is 1, but due to Stuckart fault, this line is becoming a 0. So this is D, and D bar is something like this line normally is 0, and because of a Stuckart 1 fault, the line is becoming a 1. So these are the two basic lines we introduce. So this is what is the example, you can just have a look at it. So 1 1, the answer is a D. That means maybe this is if it is stuck at 0, so normally answer will be 1 because the stuck at 0 will be 0. So this line I have to put a D. Stuck at 0, stuck at 1, 0 is x, the output of the AND gate will be a x, because I do not know if this line is a 0, the output will be 0. If this line is a 1, then the answer will be a D. So basically that means x means unknown. So in this case it is 0 0, the answer should be a 0, but due to Stuckart 1 fault the answer is a 1, so I will represent as a D bar. This is just Routh's 5-value algebra. Now I will tell you the example of how automatic test pattern generation is done and also show the example of a conflict. So this is a circuit, assume, and we have to test for Stuckart 0 at all the lines. I am just taking a single Stuckart 0 fault over here. Then what is my sensitization? So I have to make B equal to 1. Now interestingly there will be one path to propagate by this and one path to propagate by this. So, why lot of iterations will be required? Because you will have multiple options at your hand. So, you have to decide at what you have to do. Nowadays, lot of advances in algorithms have come up for such pattern generation, which will tell you an estimate which is a better path. But I am not going into such advances in advanced algorithm, because they are part of advanced test architecture, advanced VLSI test courses. Here my job is to show you the basic idea of testing and how it is applicable in embedded systems. So, all the heuristics I am not going into. So, basically which part you want to choose. So, there are some heuristics which will tell you which is the best one. But anyway, at present I do not have such heuristics at hand. So, I will take the path E, F, G, H. So, what is 1? Normal 1, fault is 0. That means what? It is D. That is normal 1, fault 0 is D by Roth's algebra. So, I have to propagate these values at the output. Now, you see this AND gate. So, these should be propagated D, and this is an inversion, it is an AND gate. So, it will be inverted to D, simple Boolean logic. So, this is sensitization. Now, I have to propagate, I have to justify this. This is sensitization, this D prime is propagation, and now I have to justify it. Now, justification means what? This is D prime, this is a NAND gate. So, always the answer of the NAND gate should be, other input should be a 1. If it is a 0, directly the NAND gate will be 1 and this fault propagation value will be lost. This is a OR gate. So, this D has been propagated to here. So, I should have a 0 over here as a justification. Because why? Because if I make a 1 over here, the output of the AND gate will be 1 and the fault propagation will be lost. So, I put a 0 over here. AND gate, of course, this has to be a 1, otherwise this will not propagate. So, it is a 0. So, how do I get a 0 in the NAND gate? So, basically there is only one choice, that is you have to put a 1 over here, as well as we have to put a 1 over here. So, but by this B equal to 1, this is D as well as this is D, but I require a 0 at the NAND gate. 0 at the NAND gate means basically I require a 1 and a 1 over here. This should be 1, this should be 1. This is 1, 1, 1 is equal. Only if the possible, this can be a 0. But now you see I require a 1 over here, but this is stuck at 0, apply 1, so D, so this D is coming over here. So, this is basically a conflict at J. So, as I told you, life is not very green, you can have lot of conflicts. So, justification tells that G equal to 0. So, J equal to, this one is equal to 0 if and only if J equal to 1. So, if J, sorry, so this is what I have told you. So, justification will require J equal to 0, but basically this is already D by this. So, this sorry, so there is already a D over here, you can easily observe over here. So, this D is over there and basically it will be a D prime over here, something like this. So, there is a conflict, or more better way to observe is something like this. As I told you, so this is a 0. So, NAND gate becomes a 0 only if both of them are 1 1, because 1 1 is 1 for an AND gate and inversion will be a 0. So, this is the only combination you have, but here is already a D. So, there is a conflict, basically this line we cannot get a 0 over here. So, there is no question of having a 0 over here. So, with that there is a conflict in this one, this case. So, this choice of path has been a problem for us. So, what I have to do? There is another path possible to do this. Had this path not been available, though we could have said this fault is a non-testable fault. But now I have another path available. So, I will use this iteration. So, I have given this example basically to show that what is an automatic test pattern generation algorithm, synthesize, propagate and justify. Also, it is giving you a picture that always you may not get, basically what I have told is that always you may not get the so called your solution in one iteration, there can be multiple iteration. So, now they have taken this path. So, 1 0. So, this is D of course, then this is inversion. So, it will be D inversion, it will be the inversion because of the NAND gate, this is the propagation part. So, D bar, again inversion is D. Now, you have to justify this. So, justify of course, this gate will be a 1, correct. Then this OR gate, the other end should be a 0. This I can very easily get to be a 0 because I can make it as a 0, but this line is also a D. But basically by making this line as a 0, I can get a 0 over here. So, this is justified. Now what? Now I can just simply put a 1 over as C. If I put a 1 over this C, so this D will be propagated here and and D prime will be gone over here. So, the conflict at G is now no longer there. So, it is a basically a successful test pattern generation. So, you see I have a 0 over here. Only interesting is that this 0 is making this line directly as 0, even if it is a D over here, this is actually blocked. So, there is no conflict happening, and similarly this is what is the idea. So, you can see this is what has been done. So, this shows you basically what is an automatic test pattern generation for difficult to test fault. Sensitize, propagate and justify. So, I have to repeat it for all such single faults, because I have done for this, I have done for this, I have to do it for all the lines, and basically your job is done. And if by all the line I means whichever lines could not be tested by the random test pattern generation algorithm. So, all the lines which were tested by the random test patterns need not be covered by this method. So, it brings down the complexity hugely, because more than 90% of the faults will be detected by the random test pattern generation. A few of the difficult faults will remain, which I have to go by this algorithm. There are a lot of, the basic algorithm is called D algorithm. There are a lot of variations like PODEM, FAN, etc., and with lot of heuristics coming into picture, which tells you that I should take this path before and not this path before, because if I would have taken a correct path in the beginning, there should not have been any iterations. There are a lot of modifications which brings more efficiency to the test pattern generation algorithm. So, they can be learned in any kind of a standard very long hardware testing course, but here I have tried to give you the gist that what is an ATPG based testing, what is the basic algorithm, and why there can be iterations and so forth. And you have to keep it and you have to keep on repeating it for all the faults till you find out a test pattern which detects it, the difficult to test faults, and finally you will also you may find out some faults for which no test pattern could be generated, because you would have exhausted this path, all the paths you would have exhausted, still you could not have got a sensitized propagation and justify successful. So, that fault is a untestable fault. So, those faults cannot be tested at all. So, with this basically the test patterns will be generated. So, when the circuit has to be tested, these patterns has to be applied physically, and the golden response in this case is D. So, in the previous case, whatever be the golden response means what is the expected response that the test pattern applied to the circuit will tell you, and that has to be matched in physical testing, and if it is proper, the circuit is correct, else there is a fault. So, with this we come to the end of automatic test pattern generation for combinational circuit. In next class we will see how things start becoming complex if there is sequential elements in this. Thank you.